What's up guys, and welcome to this tutorial on question 6 of the 2016 supplementary exam. It's called fields and it has to do with gravitational and electric fields. Okay, so let's get into it. So we start off with a definition. 6.1 says state Newton's law of universal gravitation. Okay, so the law says that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Okay, so basically we get the equation that the force is equal to G, the gravitational constant, times m1, m2, the two masses, divided by r squared. Okay. So 6.2 says a dying star has a mass of 4.5 times 10 to the 23 kilograms, is accelerated towards a black hole of mass 9.9 times 10 to the 30 kilograms by a gravitational force. So here we can say we have M1, we have M2, and we have F. And then it says calculate the distance between the centers of the black hole and the dying star. Okay, so we're going to use the equation I just put down. F is equal to G m1 m2 over r squared. Okay, then we have F was 3.4 times 10 to the 29 is equal to, G is our gravitational constant, which is equal to 6.7 times 10 to the minus 11. Okay, mass 1 we can say is 4.5 times 10 to the 30, and mass 2 is 9.9 times 10 to the 30. Okay, all over r squared. Okay, so the only unknown here in this equation is r squared, so we can solve for r is equal to 9.37 times 10 to the 10 units of meters. Okay, and we get 4 marks for that. The acceleration due to gravity on Earth, G, is equal to 9.8. The planet Saturn has a mass that is 95 times Earth's mass and a radius that is 9.4 times the Earth's radius. Determine the acceleration due to gravity on Saturn. Okay, so basically in this question we haven't been told what the mass of Saturn is or the radius of Saturn, but we've been told what it is in relation to or in comparison to Earth. So what we first need to do is get the gravitation. So question 6.3, the gravitational force on Earth is equal to, okay, so the governing equation we can say is the gravitational force is equal to the gravitational constant times the mass over r squared. Okay, so that's our governing equation. So if we want to get it for Earth, so the gravitational force on Earth is equal to the constant times the mass of Earth times the radius of Earth squared. Okay, so now if you want the gravitational acceleration on Saturn, it's going to be the gravitational constant, the mass of Saturn, over the radius of Saturn squared. Okay, and this is equal to the gravitational constant G, the mass of Saturn. The planet Saturn has a mass that is 95 times, so it's going to be times 95 times the mass of Earth over, and the radius of Saturn, the Earth's radius, and the radius, okay, so the radius is 9.4 times the radius of the Earth squared. Okay, so now what I'm going to do is I'm going to write it in a different format, which is just, I'm going to pull the 95 forward, and I'm going to take the 9.4 squared out the bottom, and then we're left with G, mass of the Earth over radius of the Earth squared. Okay, and this whole thing here is equal to that whole thing there is equal to, so this whole thing is equal to G on Earth, sorry, is equal to that thing there, which is G on Earth. Okay, which is equal to 9,8. Okay, so we can say that it's equal to 95 over 9,4 squared times 9,8. Okay, and if we plug that into our calculator, we get a value of 10,54 meters per second squared. Okay, that's the final answer. Yeah. Okay, and we get 4 marks for that. Okay, define the magnitude of an electric field at a point. Okay, so it's a definition. Okay, so 6.4. Okay, so the definition says that the magnitude of an electric field at a point is the force per unit positive charge. Okay, I'm going to note per unit positive charge. Okay, just note that might come useful later. Okay, so the diagram below represents an electric field in a region of space. It can be seen that the field lines are parallel and evenly spaced on the left, on this side, and then spread out towards the right. Okay. Compare the strength of the electric field at point labeled P, so point P and point Q. Use evidence on the diagram to explain. Okay, so 6.5.1. We can say that the strength at P, okay, so at P, the lines are very close to each other, and at Q, the lines start to spread. Okay, so we can say that the strength at P, okay, so the strength at P is greater than the strength at Q. Okay, and the reason for this is the field lines are closer together at P. Okay, so we can see in the diagram that the field lines at P are closer than at Q. Okay, and we get 2 marks for that. Okay, an electron, this is a negative charge, is placed at position Q, position X, as shown. On the thing, draw an arrow starting on the electron in the to indicate the force experienced by the electron in the electric field. Okay, so draw an arrow to indicate the force experienced. Okay, so before, remember, we said that this electric field is defined in the direction that a positive point charge would move. Okay, but now we've got a negative point charge. Okay, so it's going to move. So the field goes that way. Okay, so a negative point charge would move in the opposite direction to the field. So it's going to be tangent to this line here. It's going to look something like that. So that's the force that's experienced. Okay, let's call that F. So it's obviously going to be a straight line. Mine's obviously, use a ruler in the exam. Yeah, so that's that, and we get 2 marks for that. Okay, cool stuff. Not too difficult. 2 definitions, so 4 marks worth of definitions. Yeah, quite a nice question, not too difficult. 16 marks, and let's see, 10 minutes. So not bad at all. Okay, cool stuff, guys. Thanks for watching, and I hope you found it useful.